My name is Joseph Basic. I work for Facebook. I'm a software engineer. I'm one of the maintainers for ButterFS, NBD, the io.latency controller, a whole bunch of random shit. I'm going to talk to you about what I've been working on with IO controllers and cgroups and how we've been doing this at Facebook. So first of all, why do we need an IO controller? So this is a graph of the PSI pressure statistics for this build box, and you'll see the orange line is the memory pressure, and the blue line is the IO pressure. So you can have memory isolation, you can have CPU isolation. It doesn't really matter if you don't have IO isolation. IO and memory are very tightly entwined, so you need to have both of them working or have proper resource isolation. So why did I have to write another one? And two, in fact. Oops. Because what we had before was CFQ's io.weight. CFQ is a IO scheduler. It only worked for the single queue. Everything's on multi-queue now, and it was awful. We have io.max, which is not work conserving. You can set bandwidth and IOPS limitations for your cgroups or whatever. This also didn't seem to work super well either, and was really hard to configure. Also, even if you were using multi-queue, it took the queue lock for every bio that came into the system. So you have this, we have these nice super fast NVMe drives, and everybody is getting contended on this one queue lock anytime a bio comes through. So it was really, really not great. You sacrifice a ridiculous amount of throughput just to limit bandwidth. So I came up with a different solution, which is io.latency. And instead of making another IO scheduler, I kind of put it into the layer right before we get a request. So the way the block layer works is file system submits a bio, goes into the make request stuff. You get a request, and the request with multi-queue, you have a certain number of requests, and it's tied to the number of requests you can have outstanding for your device. So think of a request as like an actual hardware resource. The problem with implementing at the IO scheduler layer like CFQ did or any other solution would, is that you can induce latency at this point with lower level or lower priority cgroups, because if they just get to take up these request structures, they're occupying resources that the higher priority could use. So you want to stop it before it gets to this point. So that's where IO latency sits. It sits right here. So it applies per peer group. Basically what happens is you set a threshold target for your group, and everybody in that peer group is beholden to this. So that means you can have different hierarchies or whatever, and you can kind of treat different groups at different ways. And it only applies at the peer level. It's winner takes all. There's no proportionality. We tried proportionality originally, but it was kind of tricky to get working. And in the end, all we really wanted to do at that particular time was protect the workload. So the workload gets his threshold target. If he starts missing his threshold target, everybody else gets screwed. Everybody else with lower priority, I should say, gets screwed. It's meant to be work conserving. So as long as everybody's meeting their latency thresholds, nothing happens. You get full, everybody can just go and there's no problem. I wrote winner takes all twice. That's a good job. Excellent. All right, challenges and solutions. So the wonderful thing about working for Facebook and implementing kernel things is we are the developers and the consumers. I wrote the original IO latency in about 2 weeks, worked perfectly with FIO scripts, and I spent 4 months getting it to actually work in production. There are a lot of other problems that user space can come up with that FIO is not capable of enveloping. So one of the main problems that I had originally was there's no feedback system when you're under pressure. So we had this kind of classic case of like, hey, some guy starts, some low priority task starts using up all the memory. This drives the box into swap. The IO pressure from the swapping causes the workload to tank. And there's no way to like tell that this is happening. There's no way to say, hey, lower priority C group, stop consuming memory, because he's not actually the one doing the IO. It's the main workload, because the main workload has the higher priority. He tries to allocate memory or read in things that got flushed out because of memory pressure, and he's the one doing the swapping. So you need a way to feed that back into the other C group. So the way I did this was have a C group wide pressure indicator saying that, okay, we're under severe block pressure. And that way in the memory path, you can have this check to say, hey, am I being too much of a drain on resources? Okay, I need to back off. The other, and coupled with this, is the system doesn't really expect latency at submit bio time. File systems assume this is asynchronous. It is. You're supposed to just set off the bio, and they expect submit bio to be cheap. So they'll do it with like locks held and stuff, which is not super great if you like go to throttle the lower priority C group and decide to throttle it for 2 seconds while it's holding all of these, global locks. So one of the things that we had to do was devise a new way to throttle that was outside of the main IO path. And this used the similar infrastructure that Alviro put in place for fput, where we delay the throttling until right before we exit to user space. That way we can know that there's no locks being held, and we're not creating any priority inversions by throttling the lower priority C group. And ext4 has a priority inversion. We ran into this, like we got all this other stuff working and then realized that ext4 wasn't working super well for us, and it was because of the way it does ordered mode. One of the things that we had to do was we treat metadata as if it's gold, because if one guy, like higher priority guy, wants to read some metadata that a low priority guy was reading, if we throttled that IO, we're throttling the high priority group, and so that's a priority inversion. With ext4, it writes out the log, or starts the end of the transaction, and it starts to write out all of the data. And the data does have to be throttled, but because we're holding the transaction like hostage during this point, it creates this priority version. So we switched all of our root file systems to Btrfs. All right, and so I have pretty graphs. So look at that's hard to tell, isn't it? So I'll walk down here. All right, this is fbtext2. This is our C group and C group settings or whatever. And this is the baseline. This is requests per second. This is our HHVM web servers. We have them put under heavy load. Usually they're like 200 requests per second. But we jack up the load to these things, so they're up in like the 650s. All right, and this is on spinning Rust. Okay, so they're both about the same. These down here are the pressure statistics, the memory pressure and IO pressure. All right, so starting right here, we do this slow memory leak. And this right here is the box dying that doesn't have any protection. So he kind of struggles for a little bit, thrashes for a long time. It doesn't actually take this long to reboot. Probably thrashed for a good 20 minutes, rebooted, and then it takes a while for him to ramp back up because he has to like join back in the cluster and start getting traffic and all that shit. So that's what, 50 minutes to recover from this. Whereas, okay, this is fbtext2, we dip down to what, 500 RPS. OMD notices the spike in pressure, kills the consumer. We go back to normal. We start it again. Same thing, drops, pressure increases, OMD kills it. do it again. So we run this thing 3 times in the amount of time it took one box to come back. This is the same test on SSDs. It's even more awesome. There's very little drop, though the other box doesn't completely die, which is nice. So it takes, what, 10-ish minutes for the in-kernel OM killer to kick in and kill the thing. And this is with 100 megabits per second growth, so this is a faster memory leak. And you can see each time it takes longer for the in-kernel OM killer to kick in and kill the thing, and the RPS drops deeper each time. And this is just like your classic IO storm. We were obviously more concerned about memory leaks because user space is terrible. But you know, the other thing that's terrible is RPM installs. So we did this like big tar, like multi-CPU tar untarring thing, and it's kind of hard to see, but you know, we're dropping down about 400 RPS or whatever, so we're protecting us pretty well, whereas this is with no protection. You know, we're up and down to 100 RPS. And again, this is on spinning rust. I didn't put the thing in here for SSDs because SSDs just kind of, it's hard to overwhelm the system with SSDs in this way. So the way our FBTax2 stuff is set up, we have like 3 main slices. These are top level slices. Workload, and under there, there's like, that's where all our containers go. You have our widely deployed binaries, you have the Tupperware agent, which is responsible for like setting up cgroups and the container and launching the containers and stuff, and setting the appropriate settings, and then the actual workload. System.slice, that's where like Chef runs. That's the thing that pulls down all of our configurations, make sure our packages are installed. That guy has its latency target set the highest. Workload slice and host slice have this, or host critical slice have the same threshold, because we want things like if the box is dying, we want people to be able to still like SSH into the box and see what's going on. So it's on equal footing with workload slice. So if workload slice was experiencing too much pressure and missing its threshold, it wouldn't punish host critical because they have equal settings. System.slice is the only guy that would get screwed. The IO controller was, you know, the last thing that we needed, but it's not the only thing. This stuff only really works together. We have memory.low. This provides like a minimum amount of memory for the job. This is the point at which we will stop reclaiming from the main workload. Io.latency to protect the workload at all costs. And then OMD, because the in-kernel OM killer is awful. OMD is a user space OM killer. It watches the pressure metrics of the cgroups that you've configured it to watch, and you set thresholds. So basically it says, I think in our configuration, it says if the pressure metrics for memory go above 50, which means you're spending 50% of your time trying to allocate memory, it goes ahead and kills the process. The thing that I'm currently working on is io.weight. It's currently in testing. Like I said, we're at the point where it passes all of the FIO scripts, so it's like completely useless. It's doing a pretty good job passing those FIO scripts. They gives good proportional balancing. Worst case, we lose about 10% of your overall capacity with saturation level I/O. What I do basically is like start a FIO job and just keep ramping up the number of jobs until I can't get any more bandwidth out of the device, and then I start the test again with io.weight on and putting them each in a group with the same weight, and run the same amount, and I lose about 10% of the bandwidth. We're willing to pay that cost for the the higher density of applications, and like I said, this is still initial. There's some work that could be done here. Everything is lockless. but I'm still doing like 2 atomic operations per IO, so I could probably get that down and make this better. But right now we're sitting at about 10%. And again, it's work conserving. We just don't want to mess with anybody if everything's okay. And this works slightly separately, slightly differently from io.latency. io.latency was very concerned about overall latency. So from the point at submit bio happens to the point that the bio completes. That's where the latency threshold was measured. For io.weight, since we're just worried about like giving proportional access to the disk, we're only measuring the actual disk latencies. So for that, we need to calculate a saturation point. We don't do anything until we decide the device is being utilized to the point at which we need to start carving people out. And we just use some default settings for that from WBT. So like I want to say like 2 milliseconds for SSDs and 50 milliseconds for hard drives, something like that. So all of this is documented. The thing about cgroups is nobody likes to touch it because it's all kind of complicated. We've tried to make it as easy as possible. We hired a tech writer to like break all this down. We have all the graphs, we have all of our settings, we have all of the moving parts, how they all work. All this stuff is on these websites. This is just the hub. You can get to all the things. All the pressure statistics are in there, so you can figure out how to use that. That stuff is really cool. Even if you don't use cgroups, the pressure statistics are on. They're on an OS level and on a cgroup level, and you can use that to monitor overall system health. That very first slide is from one of our build boxes, and I use these to tell me if something's wrong. That's how I picked this guy, is it tripped the alarm because it was sitting above, my threshold is like 30% for memory. It was sitting above my threshold for too long. So I could go and say, oh, this box is compiling Java, and that's why it's fucked. So there's documentation about that stuff and how it works and the different fields that we have. I think that's it for me. Anybody have any questions? Awesome. Thanks, guys.